Okay, so in the previous lecture, we ended chapter 8. We spoke more about work, about kinetic energy, about power, about conservation of energy. We spoke at length about potential energy, conservation of energy. Towards the end, we chatted a bit about sources of energy. And what that did is provide us with, let's say, a tool, okay, a rather important tool. And what that tool is, it allowed us to have a way of analyzing complicated physical problems, okay, without using Newton's laws directly, or without using, our equations of motion directly. And that is very, very useful and very, very important, especially in cases, for example, where it is not possible to use those formulae. Like a couple of examples we did with non-constant forces. Okay, so that was one example. If the force is not constant, we cannot use Newton's laws directly, or maybe it's too complicated to do so. Other times, we did not have all the information needed. So in the example we did with the car with a skid mark that stops within about 30 meters, that we had enough information to find out what the initial velocity was using conservation of energy, but we did not have enough information to use Newton's laws directly. And one of the reasons is because Newton's laws are so basic, they require a lot of input. They require a lot of detailed information to be able to use them in a very meaningful and direct way. Yes, Salanud, remind me at the end of the lecture, please. Okay. Now, when we spoke about conservation of total energy in a closed system, okay, we did something, but we did not actually name it. We did not say we are doing this thing, but we did it, okay? And what that did was it gave us a limitation over how our system can develop over time, okay? So, for example, when we said the total energy is conserved and we start with 100 joules, it gave us an upper limitation that no matter what happens, our velocity cannot exceed some number, right? Because that would give us energy that is more than 100, and that is impossible because we only have 100 in this closed system. So it gave us boundaries over what is and isn't allowed and how the system evolves over time. Okay, which means a system cannot evolve randomly. Okay, it can only change in very specific ways. Anyone else has a problem with my voice getting stuck? No? Okay. Good, I'll do something. So that I don't forget, I am going to Al-Ayham, I'll come back to your question. Okay, I've written it down. I'll come back to it. Okay. So, in this chapter, we will introduce and then develop together another conserved quantity, okay, which will give us even more constraints on how a system can develop. Okay, and we call this conserved quantity linear momentum. Okay, and we will, just like we introduced the work energy theorem, we will introduce something called the impulse momentum theorem. Okay, now conservation of momentum is very useful for understanding things like collisions, when things, bump into each other. Okay, and it is just as powerful and just as important as conservation of energy. And actually, towards the end of this chapter, you will see that what happens is we use these two theorems together, the work energy theorem and the impulse momentum theorem, or conservation of energy and conservation of momentum, together to completely or almost completely describe how a system evolves from one point to another. Okay, I have opened the Q&A. If you want me to do some question or something at the end of this lecture, just type it there. Because I will forget. All right. Let me try doing something. I will reduce the quality of my video. Actually do something. Okay, Mundar, do this. Go to these three dots. Click on settings. And go to video. And in receive resolution, click on standard definition 360p, one video at a time. What that will do is it will reduce the load on your computer in receiving my video and put more emphasis on the audio. Okay. So let's start by defining what is linear momentum and take it from there. I will share. Let me just share my entire screen. That's easier. Okay. So now, when we spoke, perfect. Glad to hear that, Munda. Okay. So when we spoke about kinetic energy, and I'm going to rewrite its formula here to show a key limitation with using only energy. We said half mv squared, right? And v, velocity, is a vector, which means v is not equal to minus v. The directions are actually opposite to each other. Okay, it means that v is not equal to minus v. They're opposite vectors to each other. Now, here is the problem. Say I have v equals 10 meters per second, which means it is going in this way. And I have v equals minus 10 meters per second, which is going this way. I will call v forward and v backward. Now, ke of v forward is equal to 50 joules. 10 squared is 100, divided by 2 is 50. And ke of the backward one is still 50 joules because we have the square. Okay. And that means because energy is a scalar, it is powerful in doing some calculations, but it also imposes some sort of limitation on what we can and cannot do. Okay. So we need something else that also includes direction to tell us about some stuff. Okay. Now, like kinetic energy depends on mass and velocity, but it has more dependence on velocity. So what I'll do is I'll put 2 arrows on velocity and 1 arrow on mass. Okay, because velocity is squared and mass is to the power 1. Now, momentum actually also depends on mass and velocity, but it has equal dependence on both mass and velocity. Okay, and we define it as P equals mv. And since there is no squaring, momentum is also a vector. Okay. And the word momentum comes from the Latin word movimentum, which means movement. Okay. So it is literally, you can think of it as a quantity that describes the quantity of motion. How much motion do we have? Okay. And it is usually represented by the letter P. And this is a small p, not a capital P, by the way. So I'm just going to rewrite it this way. Okay. Let's look at a few slides just to describe the concept of momentum. Yes, I know the numbers here are different than what it is in your book, but bear with me. Your book doesn't really have good supporting material. Okay. Actually, let me do it all at once so I don't have to leave again. This just looks nicer. Okay. Linear momentum. Let's start with a very, very quick definition. Anything moving has a mass and velocity. And linear momentum, P of an object, is defined as the product of mass and velocity. P equals mv, which is what we just said. Okay. The units is just the multiplication of the units of mass and velocity. So kilograms, meters per second, otherwise known as Newton second. Okay. And very important reminder again, although I just said it, it's a vector quantity with the direction the same as that of velocity. Okay. So we cannot just add two momenta numbers like we do with energies. Okay, it's a vector. Remember that. Now, if we have 10 particles okay, or an n number of particles, each one with different momentum, we can add it. We can add all their momenta together, no problem. But remember, the addition is a vector addition, not a scalar addition. Okay, and we will speak about, you can write this down, and we will speak about it in 9.6, I think, or 9.7, something called the center of mass. Okay, we'll speak about center of mass in 9.6. We can characterize it as mass, total mass, multiplied by the center of mass. Okay, Ryan, what is the difference between scalar addition and vector addition? In vectors, we need to take care of the directions. Okay, in scalars, we just add the numbers. +1 - 1 = 0. But in vector, if I have +1i - 1j, then it's still +1i - 1j. That doesn't become 0. Okay. All right. What is the rate of change of momentum? How quickly momentum changes? We actually spoke about this back in chapter 4 or chapter 5. I think it was chapter 4. We defined the rate of change momentum as something. Does anyone remember what it was? No? So I mentioned it back in chapter 4, chapter 5, and I said, look, we will come back to this later, but we can also define, when we're talking about Newton's second law, F = ma, okay, we said we can define it in a different way. Now, if I take dp by dt and p is mv, my m comes out, and I just differentiate with respect to that time, the velocity. What is dv by dt? dv by dt is a, which means dp by dt is ma. Yeah, I'll ignore this whole center of motion thing at the moment, because I will come back to it in 9.6. Okay, but the key point is rate of change of momentum, how quickly momentum changes, okay, is our force. Okay, and as we go on, move on throughout this chapter, okay, it will become clearer and clearer why this happens. Sorry, 1 second. Okay, so if we have a figure that gives momentum and time, okay, in 4 different chunks, 1, 2, 3, 4, and the figure gives the magnitude p of the linear momentum versus time for a particle moving along an axis. A force directed along the axis acts on the particle. Rank the 4 regions indicated according to the magnitude of the force. Greatest first. What would it be? Anyone? One, 4, 2, 3. Remember, our force is the rate of change of momentum, and rate of change is always the derivative, which is always the slope. Okay, which means it goes 1, 3, 2, and 4 are equal, because here you have the biggest, here you have the biggest slope, here you have the second biggest slope, here the slope is equal to 0, and here the slope is equal to 0. Okay. Now, in which region is the particle slowing? Well, since the momentum is going down, it means, and momentum equals mv, and m is constant, it means my velocity is going down here. But in 3, it is minus slope. Yes, but remember the question asked for magnitude. This is a very, very important question. Okay, and I keep asking for magnitudes because people keep forgetting to check whether the question is asking for magnitude or not. Okay. All right. Let's think of someone who is catching a ball. Okay. Baseball, cricket, or just, you throwing stuff at your brother or sister and they're trying to catch it. And think about what are the physical processes that are going on at that point. Initially, the ball is coming, it has a mass of 200 grams, and it's coming at 10 meters per second. Now, you stop it, and your final velocity is 0 meters per second. Mariam, how do I know 1 is greater than 3? Because this one is more steep. This is more steep than this. How steep it is. This has 0 steep, this is a bit steep, this is steeper, this is steeper. Okay, now I have 2 options to do this. Okay, if someone throws something at me, I can either just catch it like this immediately, or what I can do is if someone throws it, I can catch it and bring my hand backward and slowly slow it down. So I can either slow it in 1 second, or I can slow it in 10 seconds. What is the difference between the two? Now, what you would notice is if you are into sports and if you watch sports where, catching is important, something like baseball, like cricket, okay, they usually hold it and bring it back slowly. Now, take a look at this equation, F net equals dp by dt, and try to think for 30 seconds, why do they always bring it back slowly rather than just stop it right there and right then? Good. Most of you, or whoever did this, okay, whoever answered the question, answered quite a bit of it correctly. Since it is dp over dt, or a very crude approximation would be delta p over delta t, okay, when you're slowing something down, you're changing its velocity, okay, which means you are changing its momentum, okay. Now, if you change momentum very, very quickly, it means that your force will be very, very big because your delta t is going to be very small, okay? Now, someone wrote it will hurt, which makes sense, yeah? If you stop it very quickly, you will have a very large force acting on your hand and thus on your shoulder, and that is how you get injured in your shoulder, okay, or in your rotator cuff here, okay, which is a bad thing. So what you do is you tend to slow it down slowly to increase delta t as much as possible. Your delta p is still going to be the same. If your initial momentum is 100 and your final momentum is 0, your delta p is still going to be 100. But 100 divided in 1 second, that's 100 newtons, or 100 in 10 seconds, then that is simply 10 newtons, which is much, much more comfortable. Okay. Let's do it using some mathematics. I'll just rearrange this. I'll keep dp on one side and I'll bring f dt on the other side. Okay. So my momentum is my integral of force during time. Okay, and how much time my force is acting on. Okay. Now, if I integrate both sides, dp and ft dt, on the left-hand side, I will get my delta p, final momentum minus initial momentum. On my right-hand side, this thingamabob, f of t dt integrated, is what we call impulse. Okay, and we give it the capital letter J. So J is equal to the integral of f of t dt. Okay, this is our definition of impulse, and we're going to be using it quite a bit to explain why quite a few things happen. Let's do a PIQ, and then I'll do an example from your book. A ball of mass m moves to the right with constant speed v. It bounces to the left. There's a wall here. And then it bounces to the left with the same speed v. What is the change in the ball's linear momentum? So what is J? Or what is delta px? Okay, 0, 0. Okay. We have all made the eternal sinful mistake. Okay. Let's write down the definition of P. P equals mv. The underlines means vectors. What is my P final? I will say this is positive and this is negative. So it will be P minus V, which is equal to minus mv. What is my P initial? mv. Oops. So delta P, or J, is equal to P final minus P initial minus mv is equal to minus 2 mv. Yeah. This is a mistake that many people do. We just came from the chapter for kinetic energy, and there plus and minus simply became 0 because we did not have directions. Yeah. Here we have directions. So amazingly, we don't end up with 0, we end up with minus 2 mv. Okay. Now, if you look at a curve of force and time, then J is the area under the curve. Okay. Now, if what happens here is the shapes are very different. ليش P الفاينل بالسالب? Because this is what the equation gives me. Because the direction changes. So you can think of it this way. If it was coming at 10 meters per second initially, what happened here is, 1, it went from 10 to 0, and then 2, it went from 0 to minus 10, right? So your total change is 20. This is in terms of velocity. Yeah. Now, in terms of momentum, you just multiply it with m. Okay. So now look at these two forces. Okay, these are two very different forces, yet they are something very same. Okay. On the left, in the purple one, you have a force that starts off very quickly and then trails off. Okay. On the right, you have a nice rectangular constant force for a regular amount of time. If I take the total J here and the total J here, they will be the same because the area under these two curves are the same, even though it is they look different. Okay. So what I do is if I take the total J and divide it by the total time, I will get the same number, which is my average force. Okay. So just like we had average acceleration, instantaneous acceleration, average velocity, instantaneous velocity, now we also have average force and instantaneous force. Okay. J is the instantaneous force, if you want to think of it in that way. Let's consider something. Let's consider a car where, I think this example is also here in your book. Yes, if you have something similar in your book, so this is good. Okay. Okay. Now, this car comes at 30 degrees. And then it weighs, there's a person inside it who weighs 80 kilograms. Okay, the driver weighs 80 kilograms. It's coming at 70 meters per second at 30 degrees. It hits a wall and then bounces off as much as a car can bounce. Okay, at 10 degrees with a velocity of 50 meters per second. What is the impulse on the driver due to the collision? My impulse is final momentum minus initial momentum. Now, this is very different to our previous question. Okay, in this question, we came this way and then we came back. In this one, we started this way and then we went down, but the x-axis is still the same. Yeah. So yes, initially we had this, and then later we had this and this. So the y-axis flipped, but the x-axis is still in the same direction. Okay. The x component, we'll do them separately. We'll do the Vx final minus Vx initial and Vf final, Vy final minus Vy initial separately. Okay. Now, what we will end up with, okay, is 80 times my Vfx would be 70 cosine 30 minus 50 cosine 10. This would be 70 sine 30 minus 50 sine 10. And what we will end up with is minus 910 I minus 3,500 J kilograms meters per second. Or did I make a mistake? Can someone double check? Okay, so one person got positive 910, one got minus 910. Any other mistakes I have made? $2105 instead of 3,500 joules. Okay. Okay, I have made 3 mistakes here. Okay, I'll guide you through them one by one. First thing first, change in momentum should be final minus initial, right? But what did I write? My initial is 70, my final is 50. So this is actually wrong. It should be final 50 cosine 10 minus 70 cosine 30. That's my first mistake. Now you will get minus. Okay. My second mistake is again the same mistake here. This is initial minus final. It should be final minus initial. So it should be 50 sine 10 minus 70 sine 30. But then I have made one more mistake. If you do 50 sine 10 minus 70 sine 30 times 80, you still wouldn't get 3,500 joules. You know where I made a mistake? Good, excellent. Remember, in the x direction, the velocities are both in the same direction. But in the y direction, initially my VF, my VI is up, and my VF is down. Okay. So what I should be doing instead is minus 50 sine 10, minus 70 sine 30. And this way I will get minus 3,500. Good, excellent to those who managed to spot my mistakes. Now, what is the impulse? We found the impulse in terms of components, but what is the total impulse? We will take the مباشرة أو المكملة. Dina, we have to draw it out and figure it out. Okay, there is no rule. When this happens, you need to do this. When this happens, you need to do this. Okay, so the only way to do it is to do something like this. This is my wall. This is my velocity. This is my 10 degrees. I want this, and I want this. Which one is sine? Which one is cosine? If it's not useful, we need to take 90 minus or 180 plus or something like this. Okay, there's no hard and fast rule. Okay, so we take the magnitude of this force and we end up with almost 3,600 kilograms meters per second. It should be, Dina. Yes, it should be the same. If you do it properly, it should be the same. Okay. So, Sneem, welcome back to your question. Where does it? What is 34.9? Yeah, so 3494.5 is 3,500. Two significant figures. You're correct. الطرح يتحول موجب. How? My final is 50 in the bottom direction, so minus 50 sine 10. And my initial was 70 in the positive direction, so there is no minus minus to become positive. Okay. Now, here's the question. If this collision lasts for 14 milliseconds, what is the magnitude of the average force on the driver during the collision? We said average force is J divided by delta T. So if we do this, we get 2.6 times 10 to the power 5, which, well, will kill you. Okay, this is a huge, huge, huge force. Now, here's a question. If we do the exact same thing, but we change the delta t to, instead of 14 milliseconds, to, let's say we make it 1 second. Just one. Yeah. How much will it reduce it by? Well, it will just become 3616 newtons. There's a very big difference between 2.6 times 10 to the power 5 and 3616 newtons, right? And this is why you will find that old cars, if you look at the cars that, you know, maybe our parents, our grandparents used to drive, you will find them always, when they speak, they say something like سيارات اليوم كحيانة ما تنفع، دعمة واحدة وكامل كذا كرامبلز، ما منها فايدة. سيارة أول كانت حديد، كانت قوية، تدعمها انزين شوية بتخترب، لكن ما تتكنسل السيارة. Now, while that might be correct, okay, while that might be correct, what is actually happening is modern cars are safer for the passenger inside. When car manufacturers look at the safety of the safety features of a car, they don't really think about will the car survive the crash or not. What they are thinking about is, will the people inside the car survive the crash or not? Okay, so what happens is modern cars have something that we call the crumple zone, and it's actually a safety feature. You will notice that in most accidents of newer cars, the front side of the car actually crumples during the collision. So if this is what your car looks like, there is usually a steel cage here, okay, and people are sitting inside here. And there's no steel cage in the front and the back. So what happens is, if there is an accident, la samahallah, you end up with your car looking like this, with much shorter. It crumpled, okay? And this crumple takes time. Even if we go from an immediate collision of 14 milliseconds, to this crumpling just taking a few extra milliseconds, increasing the collision time to 1 second, the force that is experienced by the person inside the car is reduced from 26,000 or 260,000 newtons to simply 3,500 newtons, which is much safer, and you are much more likely to survive this crash than if your car was rigid solid with steel and wouldn't crumple, because then your delta T would be very small. Okay. Now, I want to do one more example. Before we move, and before we go conservation of linear momentum, okay, but a couple of people saying they don't understand the idea of the chapter. The idea of the chapter is rather simple. We want a quantity, okay, that describes not only the energy content, but also the direction of motion. So we have momentum given by P equals mv, okay? It is a vector, okay? And it turns out that mv, or momentum, okay, how quickly the momentum changes is your force, okay? So just like we defined force equals, just like we initially defined F equals ma, we also define F equals dp over dt, okay? And now we are doing different things with momentum to see how powerful a tool it is, and it helps us look at how systems evolve, okay, or what happens when an accidents, for example, or when different things happen. Okay, so this is the general idea of this chapter. We're talking generally about momentum. Let me do something. Okay. Okay. Let's do an example from your book. Let's take this example, 9.1. Okay, it's a bit complicated, but I think it's a good example. So around 50,000 years ago, a rather large, so radius of 25 meters, meteorite collided with Earth. Approximate speed, 1.28 times 10 to the power 4 meters per second. Okay, somewhere in the United States. Now, the impact of that collision can still be seen today, and that's a photo of it in figure 9.7. Okay. Now, this crater, okay, is around 1,200 meters in diameter. So although the initial meteorite was only 50 meters in diameter, the crater is around 1,200 meters in diameter. So you're talking a 24 times size. Okay, it's 170 meters deep and has a rim. So the edges are actually, if you look at the photo, are not flat. It's actually going up. Okay, that goes up 45 meters above the surrounding desert plain. Okay, now we know that the iron nickel meteorites typically have a density of 7970 kilograms per cubic meter. We're going to use this whole impulse shebang to estimate what was the average force and the maximum force that the meteor applied to that portion of Earth during collision. Okay. Okay. So now we have two ways to solve this question. We can either calculate what is the force that the meteor put on Earth, or we can calculate what is the force that the Earth put on the meteor to stop it. Okay. Now, if I try to calculate what is the force of the meteor on the Earth, I have one tiny problem, is that I don't know how much Earth got actually affected. So I cannot find a mass, I cannot find a density, I cannot find an initial and final velocity because, well, it's Earth, it's rock solid, we don't know what's its movement or anything. On the other hand, I know what my initial velocity for the meteor was. I know the size of the meteor. It's finite, it's small. I know its density. I can easily calculate what force I need to stop its movement. Okay. So what I'm going to do is I am going to calculate the force on the meteor. and then say, well, by Newton's third law, this is equal to the amount of force on Earth. Okay. To start with, we draw the problem. We have a meteor. It's falling down. Okay. I'll say up is positive, down is negative. Okay. And just to make it very, very simple, I'm not going to have the meteor come at an angle. I'll say it's falling vertically down. So I don't have any angles or any headaches. Okay. So my initial velocity is some number down. Good? Okay. What is my average velocity? Sorry, average force. So I'll have meteor VI is in the minus J direction. This is all I know so far. I'll put in the numbers later. Okay. My average force will be equal to J divided by delta T. Okay. And since P equals mv and I want to know what m is, I'm going to be, it's equal to rho times volume. Okay, this is high school stuff. Volume of a sphere is 4/3 pi r cubed times rho. Okay, and now I have my full sort of shebang. Okay. Now, there's one key component which the question doesn't give you and which they just guess in the answer. Now, I really don't like guessing work. Okay. But since they haven't given it to us, we have no solution but to accept what they're guessing. So delta T equals 2 seconds. So let's do it. F average equals J over delta T is equal to P final minus P initial over delta T, which is equal to M V final minus V initial over delta T, which is equal to rho V final minus V initial over delta T. My V final is going to be simply 0 because we are stopping the meteor from moving. So it's going to be equal to minus rho V VI over delta T. Now, if I put in the numbers, okay, for rho, for volume, for initial velocity, okay, I will end up getting a force of 3.33 times 10 to the power 12 newtons directed upwards. Now, this is my average force, but remember, we said that we can have a force that goes something like this. So although my average force would be somewhere here, my F max would be somewhere up here, and they're not necessarily equal. So how do I calculate F max? The only way to calculate F max, okay, is by recognizing that J equals F of t dt from t initial to t final and do the integral. There is no other way. Okay. Now, this bit is rather complicated. Okay. They introduce an exponential function, okay, which is something you haven't done yet if you haven't done differential equations or calculus 1. We haven't finished calc 1. So I'm going to leave this bit out. Okay, you can go over it on your own time if you want. But basically, what they do is, okay, they present a function that says f equals some number e to the minus t squared over 2 some constant squared. And then they integrate it. Okay. Again, you should not expect something as complicated as this to be in your test. Okay, for you, what we could do is something like f of t equals 6t squared. And then you will have j equals integral of 6t squared dt is equal to 6 t cubed over 3 from t initial to t final. Okay? All right. Let's bring in the concept of conservation of linear momentum, and then we will end this lecture with this. Okay, we'll talk about types of collisions in the next lecture. Okay. Now, what happens if my net force is equal to 0? If I have a whole bunch of forces from different directions, but my net force, if I add up all the forces in a vectorial fashion and end up with a net force of 0. What do we know about F equals ma? If F is 0, then what do we know? What happens? A is equal to 0, right? Now, in an isolated system, if F equals 0, A equals 0, since F equals dP by dt, it also means that dP by dt is equal to 0, right? And that has two possible meanings. Either that P has two different meanings. Either P equals 0, so dP by dt would be 0, or that P is equal to constant, which means that initial P minus final P is equal to 0 because it's the same number, right? Which tells us that in a closed, isolated system, okay, where we don't have force, external forces, all the forces are internal within the system itself, our P is constant. And we call this the law of conservation of linear momentum. If no net external force acts on a system of particles, the total linear momentum P of the system cannot change. What is a good example of this? I have these two. They collide. The only forces here are between this pencil and this pen, which are actually hitting each other. So one system, not two different systems, right? So these are internal, these are all forces within the system. Okay, so no external force, which means their final momentum needs to equal its initial momentum. And it's the same with, for example, collisions. Let's take the example of a rocket in outer space. Okay, how does a rocket move? It doesn't have anything to push against. So how does a rocket move? What happens is a rocket has a combustion engine which thrusts out gases or fire from the backside. So this gas has a momentum, it's going backwards. Now, before it started moving, it was just stationary. What was the momentum? Velocity was 0, so momentum was equal to 0. Now, because there are no external forces, this gas is coming outside of this rocket itself. Okay, my total momentum has to be equal to 0. It cannot be non-zero. Okay, because it means I got momentum from somewhere extra, and we did not get anything extra here. It's coming from inside the rocket itself. So the only possible way this could happen is if this gas is plus 10, then this is minus 10. Or if this is minus 10, then this is plus 10. So the total would still be equal to 0. Yeah? So this would have m minus v, this would have mv. Okay. Now, bear in mind, okay, that these two velocities need not be equal because we still have mass. Okay, but the momenta need to be equal, and I'll show you how in a bit. Okay, so what is our system here? Our system here is the rocket plus its gas, and my external force is equal to 0, which means momentum is conserved. So P gas plus P rocket is equal to 0, which gives me P rocket equals minus P gas. Okay. Now, let's do a sample. Let's do the sample. Let's do both, actually. If we have a man that is standing at rest on a horizontal, frictionless floor, how might that man make himself move? Walking, rolling, exhaling vertically, crawling slowly, or throwing a shoe horizontally? Okay, one person said B. Everyone else either don't know or are asleep. Okay. One of the issues we have, okay, is that we don't recognize how important friction is in our life. Okay. Pretty much everything we do has to do with friction. For example, I'm holding this pen. The only reason this pen isn't just slipping out of my hand is because there is a friction between the pen and my fingers. I'm able to hold it. The only reason I'm not slipping off my chair is because there's friction between my bottom and the chair, which is stopping me from just slipping off. A problem with a truly frictionless thing is that you wouldn't be able to do pretty much anything that you can normally think of. Anything that you can normally think of, okay, is useless. Okay, so we cannot walk because walking requires friction between my foot and the ground. I would push, but I would just slip. No friction. I wouldn't go anywhere. I try to roll. Rolling requires friction between my side and the floor to be able to move. No rolling. If I exhale vertically, nothing happens. Okay, because I still don't go against gravity. If I try to crawl on all four, it still wouldn't work because there is no friction. The only thing I can do is throwing a shoe horizontally, and you can think of it as exactly the question asking, if I am an empty space, just like the rocket, what is the only way I can move? I cannot ask the rocket to walk, or to an astronaut outside the rocket. I cannot tell them to walk. I cannot tell them to roll. I cannot tell them to crawl. But if they throw something, the opposite momentum will make them go in that direction. Okay. Salim, of mass 45 kilograms, runs and jumps horizontally of a stationary 168 kilogram boat on the Gulf of Oman. Salim's velocity as he jumps, so we have a boat and we have Salim who's jumping horizontally at velocity equals 2.7 meters per second. Okay. If we ignore friction, what is now the velocity of the boat? Think of it, try to do the calculation. A whole bunch of A's, a couple of B's, okay. Most people who chose A thought because Salim went 2.7, this will go minus 2.7. They equated velocities, but they forgot that there is also a mass component. Okay, so since there is no friction, okay, and initially there is no movement, so initially my momentum is equal to 0. My final momentum should also equal to 0, and that is equal to mass of Salim, velocity of Salim, plus mass of boat, velocity of boat. Which means minus mass Salim, velocity Salim, is equal to mass boat, velocity boat. Minus 45 times 2.7 divided by mass of boat is 168 is equal to actually minus 0.72 meters per second. And this is what I meant 2 minutes ago when I told you that momentum has to be equal, but velocity need not be equal because mass plays an important role. Okay, so
Doctor,
أيوة.
can we use Newton's third law? Because this goes another direction, it's opposite.
Newton's third law applies on two different objects. Sorry, yes, on two different objects. So it wouldn't be helpful here. Okay, or actually, probably yes, you can actually use Newton's third law because the force of one will be equal to the minus of the force of the other. But your problem is you don't know what the force is here. So you can use Newton's third law, but what are the forces? You don't really know. Yeah, if you were to do Newton's third law, okay, you would find out that F equals minus F, right? FAB is equal to minus FBA, correct? So MA equals minus MA here. Okay, so mass Salim, A Salim equals minus me boat, A boat. And you will end up with the exact same thing. Okay, and then you will, after that, once you get what AB is, okay, you will need to use it in one of our equations of motion. V squared equals U squared to S equals UT plus half AT squared, or V equals U plus AT. You will need to use one of these to find what the final velocity is. But if you use the equation of momentum, conservation of momentum, All you need to do is MI/VI equals MF/PF. Initial momentum equals final momentum, and that's it. You get it in one step instead of doing 3 steps.
Okay, thank you.
Okay, it is 1:20, so we can end the lecture at this point. We will continue with section. We'll continue from section 7.4 onwards in the next lecture. Section 9.4 onwards from the next lecture, inshallah. Okay. Stop presenting.